welcome everyone in Zoom and here. This is the second class of the mini course Introduction to Quantum Groups and Hopf Algebras. As I said in the first class, I'm Gastón García from Argentina, and I have been working in quantum groups and Hopf Algebras over 20 years, so I should know whatever you want to know about this subject, so feel free to ask whatever you want, okay? If I don't know the answer, I'll just say I don't know the answer. But in general, I read a lot of these things, so feel free to ask and interrupt me whenever you want, okay? So, today we are going to see why these strange objects appear so frequently in mathematics and physics. And the idea behind that is they describe symmetries of everything, yes? If something has a symmetry of a group, as in the motions of a polygon or something that is rigid, this is described by the Hopf algebra related to the group. So it is indeed the Hopf algebra. And the symmetries of more strange objects are described with something related to Hopf algebras, which are called quantum groups or variation of quantum groups. So why is that? So we're going to see why this happens, because when we look for symmetries, we want certain properties to hold. And from that properties, we can reconstruct our quantum group of Hopf algebra. So this is the idea of today. So one class, one idea. So one idea per class. Today we're going to talk about reconstruction theory. So every time we have a symmetry, then we can reconstruct an object. So because the symmetry is the incarnation of the action of some object, algebraic object. When we reconstruct the object, then we get the algebraic thing, the algebraic object, in an abstract way. Yeah? As you know, we may see this object, the incarnation of this object in different ways. So one has to realize that if we have the symmetry with different descriptions, then one has to realize that they're actually the same object. So what we do in that case, we reconstruct the original object and we see that they come from the same abstract thing. So that's the idea, the general idea of reconstruction theory. So what we saw yesterday, not yesterday, the first class, if maybe you're looking that in YouTube or in internet, so it's not yesterday. In the first class, we talk about the relation between geometry and algebra. Actually, all the examples were about algebraic geometry and commutative algebra. And we have two functors going from one side to the other. The O functors that relates a set with functions, and we go back from functions to sets, taking the spectrum. Now, we are going to relate these things with categories. We are going to relate today algebras and categories, okay? And we are going to go up and back and down. So today is the relation between algebra and category. So we're going to talk about a lot about Hopf algebras. As I said, Hopf algebras include the theory of groups and Lie algebras. And actually, one of the first attempts to understand algebra in terms of representations or things like that was introduced with groups, trying to understand abstract groups or complex groups just with matrices. So there was an idea of Frobenius and Schur and people in the 19th century. And now the mathematics developed in its so well that we can represent almost any algebraic object with representations or matrices or things like that. So this is the way of going from algebra to categories. And in the last century, the 20th century, we have a dictionary to go back, to reconstruct our algebra object. So this is why Hopf algebras became important in the theory. And why it has the name Hopf algebras? Well, Heinz Hopf was a German mathematician who was working in topology and differential geometry. Nothing to do with physics, or well, more or less with differential geometry and algebra. He was studying actually cohomology groups or some variety, and then he saw these symmetries. And then he came up with the definition, and then they are called now Hopf algebras. They were called also by Cartier, and before him, for some people, by the name of hyperalgebras. But they are the same, because they are innocuous in the theory, okay? They appear and appear over and over again, these kind of objects. Okay. So let's recall. I will recall the definition of the Hopf algebra because maybe it is too complex to begin without recalling that. A Hopf algebra has like a dual structure of an algebra, which is a coalgebra. And think about functions on something. So the coalgebra means we are playing with functions. Yes. Yesterday, the first core lecture, I defined what is a co-multiplication, which is co-associative, and it means that this diagram should commute, and we have a co-unit that it means that this diagram should commute. And if we think about functions, the co-associativity is the dual notion of associativity on a group, and the co-unit is the dual notion of a unit on a group or algebra. So every time we have a coalgebra, the dual of a coalgebra, the linear dual, just the linear space, is an algebra. So coalgebras and algebras are related like this. The dual of a coalgebra is always an algebra, but not the other way around, because we have problems with the infinite things because of the tensor product. So when we have the two structures, algebra and coalgebra, and they are compatible, if they are compatible, then they form a bialgebra. But bialgebras are not what we want, because we want something related to groups. And something related to group has to have an analogous of inverting elements. And the analogous of inverting elements is given by the antipode. So in the first class, we saw a lot of examples, we saw some examples about this linear map, the antipode. So since the first class, the examples were about functions on something, I'm going to show you easiest examples which are not dual to something. We're going to play with duals today, but let's see some examples first. So a couple of remarks. The definition is like a self-dual definition, because I said the dual of a coalgebra is an algebra. And in some cases, for example, when the vector space is finite dimensional, the dual of an algebra is a coalgebra. So if we have something that have both structures, the dual is again same kind of object in the same family. So the dual of a Hopf algebra is a Hopf algebra if the Hopf algebra is finite dimensional. So great. We have a lot of objects like this, so we have a symmetry in them. The dual is again the object that we are playing with. So how do we construct back and forth the maps? So if you give me a Hopf algebra, so an algebra with a coalgebra structure with an antipode, then how would you construct the dual? Just as a vector space, one takes the dual. And the multiplication on one side is converted in the co-multiplication on the other side by the transpose. The unit on one side is converted into the co-unit on the other side. The co-multiplication or the co-product is translated into the product. And you see here that I put some strange symbol here. And this is a key point. This here, this is an isomorphism. And this isomorphism is true in the finite dimensional case. When our vector space H is not finite dimensional, this is not true any longer. So we had problems here. And in this case, I put the inclusion, and this is okay. So we always have here, given a co-multiplication, we always have a multiplication. This is why a dual of a co-algebra is an algebra. But on the other hand, the dual of an algebra is not always a co-algebra. So here we have a problem. So the co-unit is a unit, and the antipode gives me an antipode of the transpose. So by playing with transposes, every Hopf algebra has a dual, that is a Hopf algebra again, when the Hopf algebra is finite dimensional. And if we apply again the dual again, we go back to our original objects. So this is why I'm playing with duals, because we are playing with objects and functions on the objects. And the functions live in the dual space. So when you play, when you are working with something, and this is very good to think about functions on this something. And the functions on this something is in the dual. And this is the relation between functions and elements, and you can go back and forth between these two objects and the relation between them. And some problem is difficult by looking at the object, then you go to the dual, and then it's easier. Yeah, I have to think in that way. So, first example, just was recalled yesterday, I said again yesterday. Recall in the first class, we introduced the example of a group algebra. Then someone asked me about the ring algebra. In this case, it's the same. It's the same example. We take the group algebra, so abstract linear combination of elements in the group. And this is a Hopf algebra, where the co-multiplication is the easiest one. Just take the diagonal map. And note that the co-multiplication is a linear map. So I am defining the linear map in the basis. So this is well defined because I'm defining it on the basis. And one has to check that it's actually co-associative, but it's very easy because one has to check that this diagram commute. So we apply the co-multiplication, and here the co-multiplication tensor the identity. And here the identity tensor co-multiplication. So I will take a color, and let's pick an element G. We co-multiply, and we go to G tensor G. If we co-multiply in the second tensor, then we get G tensor G tensor G. And then let's do that with on this side, this path. We co-multiply, we get G tensor G. And if we co-multiply, we get, in the first tensor, we get G tensor G tensor G. These two things are the same for any G. Since we have a basis, then voila. This is commuted. Yeah, it's very easy to prove that this thing is a Hopf algebra. And the same one can do the same with the co-unit, proving that this thing defines a co-unit and the S defines an antipode. So what's the dual of a group algebra? So the dual, so the group is finite, say. The dual is just you take the functions on the group, on this vector space, which is the same as taking the functions on the group, because the elements of the group form a basis. This is a very good theorem of linear algebra. If you define a linear map on the basis, then you're done. Okay, so just the dual is given by the functions defined on the group. So take a dual basis of this of the basis of the group algebra, and the dual basis is the basis given by this delta, and this delta evaluated in the delta J evaluated in H is just delta GH, which that means 1 if G is equal to H and 0 otherwise. And this is the final basis of the dual. And then one can compute by hand the co-multiplication, the co-unit, and the antipole. Let's do the co-multiplication. So as I said yesterday, we want to compute the co-multiplication of this element. But I define this element as the dual of something, and this is the transpose of the multiplication. So let's evaluate this in a pair of elements of the group. Yes? So by our formula of the dual of something, this is the transpose of the multiplication. So this should be the definition of dg applied to the multiplication of these two. Yes? And now we know the definition of this thing, and we apply the definition. So this is 1 if g is equal to hk and 0 otherwise. So here we are saying that actually the k is equal to h minus 1 g, or maybe the other way around, or I don't know. Let me think. Yeah, let's keep it like this. So if we think a moment, this is true. This thing is related h and k here. So this function gives us the same as this function. So in the first tensor we put delta h, and in the second tensor we put, instead of k, delta h minus 1 g, and we sum over all possible h. So if we apply this function on hk, then we get the same result. Okay? So this function is the same as this one, and this is true for all h and k. So what we get is that actually the co-multiplication of this thing is this sum. So you see that the co-multiplication in the group case was very easy because it's G tensor G. But we go to the dual, then we get a strange formula. And this is going to happen over and over again. So we get the sum of tensors. Yeah. Okay, and in this way you can perform all computations and to compute the dual. And you get this formula. So, if we see the co-multiplication in a group, we will talk it in the first class, the co-multiplication here is commutative. It's co-commutative. We can interchange the tensors and nothing happens. All right? It is co-commutative. But the group algebra is not commutative because we cannot interchange two elements in the group. In general, we can do that when the group is abelian. So if the group is not abelian, for example, the group of rotations or something like that, which is not abelian, then the group algebra is not commutative. And we have, for those that knows about characters, the character group is a subgroup of the dual. So the group algebra of the character group is inside our function algebra and actually coincide when the group is abelian. So when the group is abelian, everything works nice. And this is more or less the model for the Pontryagin duality in analysis. But for non-abelian things, everything is strange. And actually, we're very interested in non-abelian things and non-concomitant things because it appears everywhere. So, till now I was talking about classical things, groups and functions on groups. Now, let me introduce you a new object, the Sweedler algebra. This is due to Moss-Sweedler. And this example was given before the existence of quantum groups. And we will see in the last lecture that is actually related to a quantum group. So the Sweedler algebra is the algebra generated by two elements, the g and the x, and satisfying this relation. G squared is 1, x squared is 0, and gx does not commute, x does not commute with g, but anti-commute. Yeah, this is what the physicists say, anti-commute. So it means that we have a minus there. Okay, so what is the structure? This is the algebra structure. And it could have a lot of coalgebra structure, but actually it doesn't. But I will show you one. And the one is given by the following. The G behaves like a group element. This is why we call it a group-like element. And the X behaves different. It behaves like being in a Lie algebra, but not actually. The co-multiplication is given by this formula, x tensor 1 plus g tensor x. And actually, this is defined Hopf algebra in H4. So, okay, that's a non-commutative and non-concommutative Hopf algebra. It's non-commutative because g and x do not commute. And it's not co-commutative because the x does not behave well if we interchange the first tensor and the second one. Yeah, because this is not symmetric. We have a 1 there and a g there. So by a definition that I gave in the first lecture of a quantum group, this should be a quantum group because it's a non-commutative, non-co-commutative Hopf algebra. But I don't know if this example can be seen in physics. So it's not clear what a quantum group is, so I don't know if to call it a quantum group. It is actually related to a quantum group. I will see that later. Yeah? A quantum group at the root of unity. So the dimension is very nice because it's 4. It's very small. So we have dimension 4. And the dual is itself. And as I said, it is related to quantum groups. So this was like a rush, a resume about Hopf algebras. So why Hopf algebras? Now we will see why this happens. First of all, in order to understand a new object in mathematics, what we do, we try to represent them in as easy as we can. Okay, for example, with matrices or with something that can be seen easily. This is the idea of what the people do in geometry. For them, the representation is something geometrical. So if you show them something very abstract and say it is not a representation, it should be something geometrical, something related to some geometry. And the people doing combinatorics like the representations to move something that is finite. Okay, we do the abstract way, we define representation in the more general way. So these are incarnations of our abstract object. and our abstract object has all the properties that we were looking for. So, I will recall first the definition of a representation of an algebra in general. So a linear representation of an algebra is a vector space of any dimension and a morphism from our algebra to the endomorphism of this V. What is that? The endomorphism, just the linear maps from V to V. And this is an algebra with decomposition. So it is okay with saying that this is an algebra map. So instead of saying this, maybe in some books you will find that the properties of being an algebra map are listed as below. The element 1 in our algebra, just remember that my algebras, I think I said that in the first lecture, but I don't remember. My algebras are going to be algebras with units, okay? So there is always a 1 in my algebra. The image of the 1 is the identity. The map is linear. This is the second equality. And the product of two elements goes to the composition. So I'm saying in these three properties that this map is an algebra map. All right, that's a linear representation of something. The idea is you take V, a vector space as you want, for example, the complex number to the n or any dimension, and the endomorphism of that are matrices. So actually we're seeing our algebra as matrices of something. So for those that know about this, having a representation of an algebra is the same as having a module. Yes? The module is, let me write the definition of a module. It's like a vector space, but not. Okay? The vector spaces are over fields, and the modules are over rings or algebras. So why did I wrote that strange definition for modules? Is because of this. A module, V is an A module, a left, say, a left A module, if we have a map BV which satisfy the following properties. So I will put it point, okay, with the point there, with a dot. So A acting on a linear combination of things is linear. So A acting on V plus lambda of A acting on W. A linear combination of elements in the algebra act also in the nice way. We can distribute by linearity. And then there is a nice, this actually is saying that this map is bilinear. And if this map is bilinear, then actually what we are defining is a map from the tensor product. Yes, this is why the tensor product enters into the picture. So we forget about bilinearity and put the tensor. And the last thing is, or one of the last, is if we multiply something and we act, then it should give me the same as first acting by B and then to the result acting by A. So, as you see, it's the same as it was written in the previous slide, but with a row there. So, actually, we are talking about the same things. A linear representation is a module. Yeah? So, the relation is the image of our A is corresponds to the action of A. So when we talk about representations, we mix the languages and we say, okay, this element acts as something. So it is saying it is represented by something is the same as saying it acts by something. And of course, one could translate everything in diagrams. So we have this property, the property here, we can translate it into a diagram. Yeah? If we use this notation with the tensor product, we translate it with a diagram. And the diagram is the following. I like colors. So we have three objects, A, B, and C, and B, and the other V. So in this side, we first multiply the first two tensors and go to A tensor B, and then we act, and then we land in V. Yes, what we are doing here is we are taking A, B, and the other V. Here, we first multiply the first two tensors, and then we act. This one. And the other way around, we take the other path. We act first. So it is the identity tensor action, and then we act. So here we come to A tensor B acting on B, and then we come here to A acting on B, acting on D, and this should be the same. So this is saying that this diagram should commute. So to think about categories, we have two ways. When we talk about categories, we talk about diagrams that commute. To check that the diagram commute, you can check them in elements, yeah, as I did here. And this is what we did in the first step in mathematics, okay? Or with equations, these equations that should be satisfied for any A, B in A, and V in V, is the same as satisfying the path, okay? So elements, equations, or diagrams. So today we're going to play with diagrams for getting the elements. This is a very good thing. It's very abstract, but if you get used to that, it's very good because you forget elements and you see the whole picture, yeah? All right. So, what is a morphism between two representations? Okay, is something that relates the two representations in a nice way. What I'm saying is it's a linear map that such that the diagram commute. But what is the diagram saying? Okay, the diagram is saying that if you go to the other side and act with an element, is the same as acting before going and then you go. Yes? So, in other terms, is that the action commutes with the map. Or that the action goes out. Okay? It's like saying that it's alinear. Some people call it alinear. So, but in terms of diagrams, you see the things like this. So I'm moving to diagrams now. So if you have time after the lecture, you can check it in elements and what I'm saying with this. Elements and equations. You have two translations of diagrams, which is more or less the same. Okay. So you have to check that it's commutative, the diagram, okay? Not the algebra, the diagram. We talk about a commutative diagram here. So, okay, we have An algebra, the algebra has representations. We always have representations. And we have maps between the representations, functions. We call them morphisms because they respect the forms of the things. Morphisms, the structure. We respect the structure, so we call them morphisms. So these two things defines a category. Objects and morphisms, or objects and arrows in general terms. So they form a category, and given an algebra, we call Rep A the category of representations, which is the same as the category of modules. So we have two expressions in literature, which is called Rep A or A mod, AM, which is A mod, left A module. And I will write Rep A with this small r when I'm talking about the category of finite dimensional representations. It turns out that depending on the algebra, these two things can be quite different. For example, for some Lie algebras, we know all the category of representation of finite dimensional representations over the complex number, but not for general things. So being finite dimensional is important if we want to know something. Okay. Of course, as I was talking about, a Hopf algebra has a duality. So it is an algebra with a coalgebra, and we can dualize because the dual of any coalgebra is an algebra, and sometimes the dual of an algebra is a coalgebra. What is the notion of the dual of a representation? Just we invert the arrows. It's a co-representation. So a co-representation is a vector space with the map going the other way around. So I come here, and instead of writing this, I write, so I raise the arrows in this direction, and a co-representation is something going the other way around. And the co-representation should satisfy this action. I invert the arrows, and instead of putting the multiplication, I have to put the co-multiplication. And instead of putting the action, I put the co-action, which I called lambda. Lambda because of left. This is an L. And the other diagram is with respect to the unit. So what you may are asking now, why the hell do I have to define this strange thing? Because the representations sometimes are difficult to find, and the co-representations are always locally finite. What does it mean? That any element is always in a finite dimensional co-representation. So they're actually better. So if you start to think about co-representations, then it's very good because you have a lot of nice properties that representations do not have. And we're going to use both to reconstruct our objects. Representations and co-representations. I will show you in a couple of minutes an example. So the proposition is the following. Why Hopf algebras or quantum groups are so special? Because the category of representations or the incarnations is very nice. For example, given two objects that are representations, we can give to the tensor product the structure of a representations. Or, in other words, if the algebra acts on two objects, then it acts on the tensor product. And why is that? Because there's the following thing. What do we need? So we have two objects in our category of representations, say. So we want to act on the tensor product of them in two elements. Say, okay? Say we have, say, take V in V and W in W. And suppose we want to act on them on the tensor product of them. So actually, what we are needing is a way to decompose H in two legs. One acting on the first tensor and the other one acting on the second tensor. So it is very natural to ask, okay, we need to decompose our H in two things. So this is why we need a map that goes from H to the tensor product of H, because we want to decompose it. So this is actually what we do. So I wrote the first class in an abstract way, the map of H going to this one. So we define H1 acting on the first one and H2 acting on the second one. So this is why we need the co-multiplication. So every time you see that you have representations of something, or you have operators on something, and you want to multiply the operators, what you are looking is to the tensor product of these things. And if you want to act on the tensor product, then you need this map. So this is why the co-multiplication appears. So, and why does it have to be co-associative? Is because the co-associativity is related to the fact that if we write the tensor product like this, say V, U, V, W, we have three components. This thing is the same as this thing. Yeah? This should be the same. And this is related to a co-associativity. This is delta tensor identity, identity tensor delta composed with delta. So every time you have the product of two representations, then your algebraic object has a coalgebra structure. This is why the coalgebra structure appears. This is a shadow of the representation. If we want tensor products, we need coalgebra structure. If we want the field to be a representation, this is again, we need the counit, because how do we act? Let's change the color. How do we act on a number? Okay, it should be a number. And if this is linear, this should be lambda h acting on 1, because lambda is lambda times 1. So actually, what we need to define is this h acting on 1, and h acting on 1 should be a number. So this defines a map from our algebraic object to the field, and this is the counit. So the counit appears when we want that our field is a representation. And why do we want the field to be our representation? Is that if we can multiply representations, then we want the representations that do nothing. So it is the unit of this multiplication. And the unit of this multiplication, in this case, is the field. And okay, we can multiply representations, that's okay. We will have a unit that is the field. Okay. Do we have inverses? So what is an inverse of a representation? It's not the number, okay, or a function. It's a vector space with something of matrices. Okay, like the thing that is related to the inverse is the dual. So if every time you have a dual, or what is called in different areas of mathematics, the contragradient representation, it means that our algebra has to have an antipode. And this is why the Hopf Algebras appears everywhere, because when we are studying representations or incarnations on something with these properties, then Hopf Algebras appears. And if we sum up all these properties, we are saying that our category is a tensor category. Of course, as I said, the dual notion of modules or representations as co-representations, they satisfy the same properties. So going to the dual in a Hopf algebra, if the algebra is finite dimensional, is very okay. We get the same things. And if it's infinite dimensional, it's more or less the same things. We have to be careful, but you get analogous properties. So, what is, how do we recognize something that it is like this? So, you have representations on something, linear maps with things, and you recognize such properties. So, what else should they satisfy in order to be related to a Hopf algebra or something, or a quantum group or something related? Okay, this was done by a lot of people, and to sum up, all the properties are in the definition of what is a tensor category. Yeah? I took this definition from the book Tensor Categories, from Ettinghoff, Jelaki, Nishchik, and Ostrich. And everything I said can be found there or in a lot of references that one can find in the references in that book. And it's the modern way of seeing this kind of things of quantum groups and Hopf algebras. So, what is a tensor category? What do we need to have a tensor category? We need tensors. So we need, the first thing is our category has to be monoidal. The monoidal thing is, all right, we have to have a tensor product. We have two elements and we want to multiply them. So this is given by a definition of bifactor. We have two elements and then the result is another one. And we put, because of the examples, we put tensor in them. All right, but with all, we want also to sum elements, not just multiply elements. And if we sum, we want also to have kernels of maps and co-kernels, quotients of things. And this is summarized in the concept of abelian. Any abelian category, this is a very big theorem, any abelian category with some properties, that it's not so important to tell you now, it's a category of representation of some algebra. Okay? Any abelian thing. So, K-linear is that the things are linear vector spaces. The things. Which things? The maps between two objects and the composition is a linear map. Okay? It is locally finite, meaning that the length of any object is finite. For example, for vector spaces, the length is the dimension. So we have finite dimensional vector spaces, and the dimension between the functions between the two is finite dimensional. And we have duals. So up to now, if you want to see examples of this one, think about the category of vector spaces. We have tensor products, we have direct sums, the maps between two vector spaces is a vector space, and the maps are linear. If we are talking about finite dimensional vector spaces, and if the vector spaces are finite dimensional, the endomorphism between them has a finite dimension. We have duals. This is a very difficult thing for students in the first years to understand about duals. And the last thing could be more strange. The endomorphism of the one object is the field. Yeah? If it's not true, then the category is called multitensor. But it's saying that, for example, if we think about vector spaces, the unit object is the field, how many linear maps do we have between the field and the field? Just numbers, and the numbers is given by the field. So the easiest tensor category that we know, is the category of vector spaces. So this is our simpler objects in the theory, vector spaces. So if we want to understand something complicated, we are going to relate it with the category of vector spaces. Why? Because we know vector spaces. So if we have something strange here and we don't know what is going on, we want to relate them with vector spaces. And this is what we are going to do in the next hour, okay? So the thing is, if you give me an abstract tensor category, or you have a problem in physics or in I don't know, in chemistry or something like that, and you recognize some of these properties, then you think, aha, if this is a tensor category, so we have these properties with different definitions, there exists a Hopf algebra such that this is the representations of these objects. Well, if the tensor category is finite, I'm going to tell you what finite is, the answer is yes. And we know how to construct the algebra H, and this is the reconstruction of H. So, as I said before, the idea is to relate C with the category, the easiest examples of tensor category of vector spaces via a nice functor. And as I said before, I'm going to follow the definitions and theorems from the book of tensor categories of Ettinghoff, Jelacki, Nikschit, and Ostrich. Okay, now it's time to make a pause or questions, yes? So we make a pause till 4 p.m. here in Trieste. I don't know where you are. 10 minutes, more or less. So first question coming. What is important of rigid here? Because we need duals. This is why I tell you rigid. If we don't have duals, then the object might not be a Hopf algebra. If we don't have tensor products or things like that, we know that if it's a Billian category plus something else, is the category of modules over an algebra, but we don't know nothing more about the algebra. So the duals, the rigidity is because of the duals. We need the antipole and duals. And I'm not saying this loud, but I'm thinking about also strict categories. What do I mean by strict categories? This thing. That between the tensor products here, we have an equality, yeah? In general, you may have an isomorphism, and then we have maps in there, so it's a bit more technical, but the idea is the same. Yeah. Another questions or remarks or comments? So think about it, and you can put it on the chat, or just ask me, open your microphone and ask. The length. The idea is, why do we need the length? This is based on the theory of groups, or maybe in algebras. The most nice situation, the nicer situation is that when you have a representation, then this representation could be decomposed into the sum of, say, a couple of another ones that are simple. What is a simple representation or irreducible? The ones that you cannot reduce anymore. And if you can do that with all V, this would be great. But in general, this is not true. So this is true when our algebra is called semi-simple, or in some cases it's called reductive. And so not all algebras are semi-simple or reductive, so this is not true. You cannot decompose always your representations into sum of simple objects, yes? It's like numbers. You would like to decompose your number into the product of elementary particles of the numbers, which are the primes. Here, the elementary things are the simple representations. So if you can do that, you understand perfectly the category, just by knowing the simples. It does not mean that it's trivial, but you understand more. On the other hand, you can always find a simple object inside your object. But maybe you cannot find another one that is in direct sum. So what do? You look at the quotient. And in the quotient, then you find another simple object, call it V2. Yeah? But since V2 is in V1, what you're getting is there exists another V2. I will put the same, say this is one, V2 tilde. There's another V2 containing V1 such that when you make the quotient, it's simple. And you go on like this, and like this, and you hope that at some point you stop with V. And this is the finite length. This is saying that any V has this decomposition, and you would like to decompose your V as a direct sum. But if you don't have that, you would like to have such a sequence, and the property is that the quotient of these objects is simple. So this is called the length. If this sequence is the best you can do, is the Jordan-Helder sequence, then you call it the length. So asking for the finite length is that. So is a step, one more step as asking that you can decompose it into the sum of simples. So this is one step more. Yes, it is like, yes, it's the same idea, the very same idea of the normal series of a group. Yes, exactly. And the idea of a normal series is to understand the group using subgroups. Yeah. Okay, is there another question or remark? If not, we continue. Remember, you can write me an email in case you have some questions or doubts about something. So up to now, what we did in the first lecture and part of this one is any geometrical object can be understood using algebra. And how? You look at functions. And once you have the algebra, how can we understand the algebra? Okay, you take representations. Yeah, you look at the things as they were matrices. Okay, and suppose we have a representation, a category or something that behaves in a way that we know. Like we can multiply things, sum things, and we have duals. So the question is this category of representation or category, strange category, related to representations of something? And the idea is yes, it always does. And this is called the reconstruction theory. And this is the reason why quantum groups and Hopf algebras and objects related to that, weak Hopf algebras, quasi-Hopf algebras, and Hopf algebroids and things like that appear in nature because the representation category is everywhere. So, what's the nice property that we are looking for a category, the relation between a category and the category of vector spaces? Now, the category of vector spaces is the category that we know a lot of things. Actually, the course in linear algebra is about understanding the category of vector spaces, okay? So the first course in algebra is understanding the category of vector spaces. And now we are saying we have a strange category. Yeah? For example, the category of representation of a group. This is another course. Or category of representation of an algebra. This is another course. So we have strange things, and we want to relate it to the easiest one, the vector spaces. So what's a nice way to relate it? So what we need is something that takes any object to a vector space, okay? Then takes the unit object that we have in our tensor category. We have a unit object, recall, and give us the unit object of the vector space. This is the field. And behaves well with the properties that I gave you with a category that is tensor. Okay, what are the properties? It's abelian. So direct sums should go to direct sums. Kernels and co-kernels. So it means exact sequences has to go to exact sequences. Or say kernels, kernels, co-kernels, co-kernels. And this is encoded in the word exact. And of course, we want this F, this way to relate these two categories, to be injective or to not missing something. And this is the word faithful. Yeah? So when I'm talking about exact faithful, I'm saying all the properties that we have, but not the product, are preserved nicely into the category of vector spaces. A way to relate two categories is by functors. So what is a functor? The functor takes objects to objects, morphisms to morphisms in a nice way. And we ask this functor to have a nice property with respect to the tensor product. So tensor product should go to tensor product in the category of vector spaces. And the thing is, it should satisfy all the possible combination of doing three tensor factors, three tensor products, and more, but with 3 is enough. And this is given by the diagram. The following diagram is the product of 3 objects as vector spaces should come from the product of let me explain this one. The image of the product of the first 2 times the image of the third one, and is the same as the image of this tensor product in C. And if we can do the other way around, and the thing is, it should be the same. Yeah, it's quite formal, but this thing should be satisfied. Yeah, and we have a lot of examples that this J is not the identity. And when you find this J, for example, actually in the definition of quantum, in a lot of constructions of quantum groups, this J is very particular. So for a given j, we find a new object. And this is called a quantization. And it depends on the j we are finding here. So in physics, sometimes it's related to the R matrix or something. And this is this j, is this relation. So in the book of Ettinghoff, Jelaki, Nishtik, Jostrik, there is an example explaining why this j is important. Okay, example, because this is a strange definition. So if you take a Hopf algebra and you take the forgetful functor is you forget. What do you forget? You forget that you have actually representations. You forget everything and you take the vector space. Okay, that's a vector, take the vector space, and that's it. And that's a fiber functor. So every time we have a category representation of a Hopf algebra, we have the forgetful functor into the category of vector spaces. So we can relate our category to the category of vector spaces. So when our category is finite, it means that is the category representation of some algebra. I told you when our category is abelian with some other properties, it's always the category representation of some algebra. So, for example, this is the case of, I'm saying we're taking the finite tensor category. This is the case with A finite dimensional. And we take a fiber functor. The very big thing is the following. The natural transformation between the functor with itself is an algebra. Oh, what is that? Okay, this is quite... The thing is, this might be seen as quite abstract, but actually it gives us the answer of everything. What is the endomorphism of a functor? So, you have two categories, C and D, say. And you have a functor going from one to the other. For, say, the forgetful functor, forgetting things. What is a natural transformation of f into itself? One writes in categorical way something like this. Eta is a natural transformation. And eta is for natural transformation. So, is that a map? No, because these are functors. So, if you want to understand that, you go one level below, and the idea is you take one object, and given an object in, say, given an object in C, you may take F, the object in D, okay? Takes objects to objects. And the natural transformation is something between a map that for any x, it gives us a map between the image of x and the image of x. And why it is called natural? Because if we have a map between x and y, say f, then it behaves well with the map. So, as I said, a functor takes objects to objects, x to fx, y to fy, and maps to maps, f, the map f to the map f to f. This is a functor. And the natural transformation is a relation between the images of the objects. And to be natural means that this thing has to commute. So, for the natural transformation, is, say, if you want, a lot of maps for any objects that behaves nicely. This is the compatibility condition between all of them. Okay, and why it is an algebra? Okay, because we have the identity, natural transformation, yeah, is doing nothing, and we have the composition. If we have two linear transformations, then we compose them. So how do we compose them? As usual, we take first one and then the other one. If you take first for the object x, eta x, and then gamma x, then you compose them as anyone knows and give us the composition. So this should be gamma composed with eta x. So this is very abstract, but it is based on thinking about functions. So if you think about functions, everything could be written very nicely, and the idea is it contains the information of the elements and the algebraic structure. So don't worry, you have to get used to that to understand arrows and things like that, because in a very example, you take examples and then these things are going to be very concrete, and then the object will appear. So the maps will appear. So where did I, okay. So the theorem is the following. If our category is a tensor category and the functor is a fiber functor, our H is actually a finite dimensional Hopf algebra. Ta-da. So this is known as the Tanaka-Klein reconstruction theorem for finite tensor categories, not for anyone. So we have a bijection between finite tensor category with fiber functors, of course, up to tensor equivalences and isomorphisms of things, and the category of finite dimensional Hopf algebras. And the category, and finite dimensional Hopf algebras. Again, the correspondence is you give me a category with a functor, with a fiber functor, then I give you a Hopf algebra. Which is this Hopf algebra? The endomorphism of the functor. So there is a very explicit formula. What do I mean by very explicit? It's not so easy to compute the endomorphism of a functor, but it's doable, okay? You know what you have to do. Then another thing is doing it. It is very common in representation theory. You know a lot of theory, but when I give you an example of a category or an algebra, just write down all the representations. It's not so easy. Sometimes it's very difficult. Are books written on representation of something? So it's not so easy. But in any case, we get the Hopf algebra. And if we have a Hopf algebra, then we can get back a finite tensor category, but taking the finite dimensional representations with the forgetful functor. So this is called the Tanaka-Klein reconstructions, or why do Hopf algebras appear in nature? Because they are the algebraic counterpart of a nice category. A category having products, sums, a unit, and duals. And in almost anything that one wants to study appear these kind of structures. For example, in conformal field theory or quantum conformal field theory, one has such structures of tensor products, duals, and things like that, then it means that some Hopf algebra is behind. Or in variants of knots and things like that, then the same happens, and then there should be Hopf algebra something in behind. Yeah. Okay. So this is the picture for finite things. So the idea of this lecture is Hopf algebras and quantum groups appear in nature because they are in nature. We have representations of things, symmetries that satisfy all these properties. And this is in a very formal way given by the idea of tensor categories. So symmetries in something, we describe it with a tensor category. And the tensor category is the category of representations of a Hopf algebra or a quantum group. This is why it appears. So now we go into the last part of the lecture of today, and the question is, okay, what about the infinite things? Because in the first lecture you gave me a lot of examples of things that are not finite. The functions on matrices, they were polynomials. The polynomials in n squared variables. This is infinite dimensional, so it's not the case. What is going on? Okay, we have a Tanaka-Crane reconstruction theorem, but we have to use duals. And as I told you, the dual is a problem. So there's a question coming on. What is the coproduct here? Yeah, it's complicated to say in a few words, so I'm going to skip it. Sorry about that, because I will not, if I start saying about this, well, the time goes by. In any case, it's there in the book. You can have a look at that, but it has a coproduct, okay? Yeah, it's a big theorem, okay, that the endomorphism of a finite dimensional Hopf algebra, the endomorphism of a fiber functor is a finite dimensional Hopf algebra. It's have a lot of pages. It's not so easy. But a very good question. Of course, it has to do, also, and I was saying that I was not going to talk about it, but I am going to talk about it. The idea is your category has a tensor product and a tensor structure of the functor. And this is giving you the coproduct of things, okay? If you don't have tensor products, you have only an abelian category, then you have only an algebra. This is a representation of an algebra, and that's it. But if you have more structure, the structure comes from the tensor product. And because you have duals, then you have the antipole. This is the idea. Okay. So, going to the infinite dimensional case, and this might be important for the people doing analysis because they like the quantum groups appearing in the infinite dimensional setting. Infinite dimensional setting and the semi-simple setting that I erased. Okay? These two properties are nice for people doing analysis or operator algebras. So let's have a look at that setting. So when our Hopf algebra is infinite dimensional, the dual is not the Hopf algebra in general. Why? Because we have problems with the dual of an algebra is not the coalgebra in general. Why? Because in an algebra, we have the multiplication. If we dualize the thing, we get a map. Let's put the arrow in the other direction. We check the transpose, and then it gives us a map to the dual of the tensor product. But the dual of the tensor product in general contains strictly, so it's not the same as the tensor product of the dual. And this is the problem, because our map should be landing here, not in there. What did I say is the other way around, or no, like this, yeah? It's not the same. So the idea is we could land here, but we actually want to land there, which is a subspace of that. So we have a problem. So what do we do to skip that problem, that issue? We look for another notion of dual so that we have this property. And there are a lot of notions of dual depending on what you do. So, if, for example, in analysis, you look at the Pontryagin dual, but we are going to look at the following dual, the finite or restricted dual. What is the finite or the restricted dual of something? Is a subspace of the dual. Which subspace? Okay, we take the functions that are zero on a big ideal of H. What is the meaning of big? The meaning of big is that the dimension of the quotient is finite. So the ideal is of finite codimension. So I'm saying finite codimension by saying this thing. So the idea of this function is you take all the functionals that are zero almost everywhere, yeah? Almost everywhere. Of course, if our algebra is finite dimensional, all functions satisfy this. So this finite dual is the dual. But in the infinite dimensional case, this is not true. So this is a subspace. And what is very good is that this dual is indeed a coalgebra. So great, we have a coalgebra. So given an algebra, the finite dual or restricted dual is always a coalgebra. So if we have, moreover, a Hopf algebra, the finite dual is a Hopf algebra. So great. So we have problems with finite dimensional things, with infinite dimensional things, but now we know how to play with it. Yes? We know how to go to the dual case. Example, take a Lie group, or a simple affine algebraic group. Take the tangent space or the Lie algebra corresponding to this Lie group. For example, if you don't know these words, don't worry. The group take the matrices of determinant 1, and the corresponding Lie algebra is the matrices with trace 0. So matrices with determinant 1 are related to matrices with determinant 0. The finite dual of the enveloping algebra, the algebra, I'm going to talk about enveloping algebras in the last lecture, is exactly the algebra that I defined in the first lecture. So we recover our algebra as a dual, as a finite dual. And what about if we dualize again? Yeah, let's dualize again. It's not true that we get the same object. Then something is inside, one object is inside the other. So in general, we have more properties that they should be satisfied, so we get the same equality. So, but nevertheless, we have a notion of duals. So, okay, as I said to you, as I told you before, if our algebra has finite dimension, then the notion of duals coincide. So, okay, very nice. We have to compute these functions. Okay, let's go back to the definition. These functions. How do we do that? Okay, this is, I don't know. It's maybe too complicated to say. This is a formal thing to define the things, but we don't know how to compute them. We have a way, and the way is related to representations. Yeah, we compute the dual using representations. So everything you compute using representations will give you the dual. This is why all the definitions used in representations in different books gives you sometimes the dual objects you are looking for, because it gives you the dual. And let me introduce this notion. How do we do that? Take a Hopf algebra and take a representation. So for any representation, we define the matrix coefficients like this. Yeah? It's a function from h to k given by this thing. And why a matrix representation? A matrix coefficient. Let's do a calculation. What is a matrix coefficient? So we take V, a vector space. So take in V a basis. Say we have dimension n. Yeah. I take the dual basis. I will use the notation is physics. I will put upper and supra indices for the dual, or I will take, no. I will take the F's. Sorry for that. I will take the F because I will going to use the F's. These are the dual bases. So if we have an action of an element on a basis element, so the very first things that we learn in linear algebra is that if we transform an element of the basis, it's a linear combination of the element of the basis. Yes? And we look, okay, let's put the element Aij. And how do we compute the elements Iij? So these elements are the elements of the matrix. So the matrix with respect to H. So our transformation of H in the basis B is our matrix Aij. Okay, this is linear algebra. We take a basis and we represent our linear transformation as a matrix. But look at this equation. If in this equation we want to know who is this, we apply the dual basis of this one to get the element. So we apply Fi to this side, and then if I apply Fi to this side is F to this thing. Since everything is linear, the F is going inside. And I should have used another letter. Okay. I want to use I and J. Maybe let me put K here. So you will see. Maybe if not, we can get confused. Let's put K. So when we are right here, in here, this is 1 if A is equal to K and 0 otherwise. So this is delta IK. And if we put this delta IK, then we get this is K, Aij. So from there to here, we get that Fi, that our Aij, our element in the matrix, is Fi of H acting on Bj. And this is exactly the definition of my matrix coefficient in H. So it is a matrix coefficient. Yeah? With respect to elements of a given basis. So the idea is, okay, do it for any linear map and any vector, and then is a matrix coefficient. Yes? So this is why it is called a matrix coefficient. Okay, so this is a map that goes from H to K. And since the image is in the field, it kills a lot of things. So the image, this element lies in the finite dual. So for any, look, what have we done? For any representation, for any f, for any v, we find an element of the finite dual. So we can do that playing with any f and any v, and this gives us a map. And the map is actually the dual of the representation. Yeah, this is an exercise, just think about it, but this is the dual of a representation. And I'm thinking about this, another exercise in linear algebra. The endomorphism of any vector space is isomorphic to the tensor product of the dual with itself. If you do that, then you understand this linear map, where it comes from. So matrix coefficients are the same via dualization as the representation. So you can understand representations looking at matrix coefficients. As I told you before, the image of our matrix coefficients are in the finite dual, and voila, the image of our matrix coefficients is a sub-coalgebra. So what? So let's play it again. Let's compute the co-multiplication. So, and again, take a vector space, the basis and the dual basis, and recall that for the dual basis we have the Fi, and Vj is delta Ij. So what is the coproduct of something like this? Yeah, okay, we don't know. So the coproduct of a function should be the product of on the other side, okay? This is a function on the algebra, so we should evaluate the coproduct into the tensor product of two elements in our algebra. So by definition of the coproduct in functions, this is the transpose of the multiplication. So this is the matrix coefficients of the product. And the matrix coefficient of the product is the product acting, I forgot to write B, f of the product acting on V. Okay, that's it. But this thing is by the action or the axiom of action is the same as this thing. And now we write this thing as we did before. How do we understand the KV? Okay, if we have a basis, this KV, we write, I will take 2 steps to write this. This KV is a linear combination of our VIs, okay? And we learn in linear algebra that the linear combination of our VI is given by the dual basis. So this is Fi, the I, the same I, or evaluated in our vector. This is a number, and This is our BI, yeah? And so I replace these things in here. So we have f of the sum of I of fi of k tensor v of h tensor bi. Yeah? All right, I forgot to write the parenthesis here. And this is the sum of I from 1 to n of fi h b of f h bi. But this one, the first one is the definition of the coefficient, the matrix coefficient of, let me write it, the matrix coefficients of fi b acting, evaluating in H, and the second one, I should have written in the other order, sorry, is the matrix coefficient of FBI evaluating in H. Yeah. So now, if someone was a K, someone has noticed that or not? No. So I have to clean it. So where is the here is the K? So here we have a K. So here we have a K. So this is actually the sum of the tensor product of these two matrix coefficients. No. I will write it. I don't know where. Let me write. I don't have the space here, so I will put the star. And the star is here. The star is, this is the tensor product of the linear, of the matrix coefficient. This one. This one evaluated in H tensor K. So, yeah, and since I begin with this thing, what we actually have, putting this thing together, since the evaluation on H tensor K is the same, then we have that the co-multiplication of any matrix coefficient is given by this formula. So we need a finite dimensional basis. And is this always possible? Yes, indeed. So matrix coefficients form a coalgebra because our object has the notion of algebra. So the matrix coefficients are a coalgebra, and they are, maybe it doesn't look so natural, but it is natural. And if you look it carefully, this is the same example as I gave you in the first lecture, where my xij was simply some matrix coefficient for some linear map. Okay? Exercise, find which one is. Okay? So the xij that I gave you in the first lecture are matrix coefficients. So the matrix coefficients are great because we have matrices, and the thing is, these maps are the maps giving you the entries of the matrices. But we think about them about maps. All right. So you can compute anything. So as I told you, we are playing with arrows, objects, and things like that. But if you want to compute, you can sit down and compute. I'm computing a little bit in the lecture. I cannot compute everything because we don't have enough time. But if you have at home, you can do it. Okay? If you're at home, you can do it later. So proposition. So I told you that the image of these matrix coefficients lies in the finite dual. But how do we get the finite dual? Okay, sum all matrix coefficients, all for all representations, yeah? And this gives you the finite dual. Wow, amazing. What's the problem in this construction? Maybe we don't know all representations. So if our category has nice properties, maybe with some representations is enough. For example, when the category is semi-simple. But if not, we have to be careful how do we can compute this element. So the proposition says that our finite dual is the span of matrix coefficients of finite dimensional representations, which is the same as finite dimensional co-representation of the dual. So sometimes in quantum group theory, one uses representations, sometimes co-representations. Okay, if we write, as I told you before, the image of each linear map, we can write the image as a tensor product, V star tensor V, okay, for each, because it gives us an endomorphism of, the thing is, I will write it here. Our C goes from no, what? I forgot what I wrote there. There. So we take the structure here to the other side. So we think something like this. So for any vector space, we think the image as this thing. And why? In this way, we get what is called the Peter-Weil version of the finite dual. And this is the definition in some cases for quantum groups of orthogonal type. This is the definition of our quantum group. You check the representations and you do something like this. Okay, it's too abstract and too difficult because we have to know all the representations. Okay, this is why sometimes you ask the category semi-simple, because with the simple representations you know everything. And sometimes with only one representation we can describe all of them. So with only one, we describe all of them. This is a case of SLN. What is good in this description? We are relating here the course, more or less. This is the two lectures. An algebraic object, this is the dual of something, with representations. So you give me representations, and I construct an object. What do we need to construct these representations? Duals and tensor products. So if we have the category with duals and tensor products, we can reconstruct an element. Yeah, magic. So if you give me that, we have an object. Yeah? And we obtain this object as a Peter-Weil version. Okay, so let's do that. This is called the Cohen construction. The Cohen construction is the following. give me any tensor category with the functor, which is exact and faithful. As I told you before, the idea of having an exact and faithful functor is you give me a category of things. Yeah? The things can be anything. But you have to have a relation from this anything to a vector space. This is the functor. To be exact and faithful means it is more or less injective and takes me sums to sums, kernels to kernels, and things like that. So the coend of this functor is the same as I wrote before. You take the image of the element, the dual, and construct the sum as I did before. And this is given by this sum. The most general case, and this is for any element in the category. In the most general case, we have to divide some E. What is E? The E is the relation that our objects behave well with the play, that with the game that playing with this transposition, the transpose maps, going from one object to the dual. Yeah, I was playing the two lectures with these maps, with co-multiplications, multiplications, something like that, and the E is that in this is the case. Okay, if it is not the case, you have to divide this E. Why in the example before there was not this E? Because these two things are always equal. Yeah? Maybe in some category they are not equal, so you have to divide it. So in mathematics, something is not equal to another thing, you divide by the relation. Okay? So the coend is always a coalgebra. As we know that the end is an algebra, the coend is always a coalgebra. The dual of the coend is the end. The end is the one I defined before. And one can construct the coend as a direct limit. And this is why the coend is better than the endomorphism. Because you construct your object as with the small, you construct the coend with the small objects that you know. But for the endomorphism of a functor, maybe it's more difficult. So the co-things can be constructed using small things. And if C is a tensor category with a fiber functor, so a functor with the properties that I told you before, exact, faithful, and has a tensor structure, and we land in the category of vector spaces, the coend is a Hopf algebra. Voila. So, given a category with these properties, we have a Hopf algebra. And we have a reconstruction theorem, a Tanaka-Klein reconstruction theorem in this case. So we have a correspondence between tensor categories with a fiber functor and Hopf algebras. You give me a tensor category with a fiber functor, then I construct the coend. I construct, yeah, but it's possible to construct. It's easy. It's easier to see the coend, who is the coend, as seeing who is the end. And if you give me a Hopf algebra, then I can construct a tensor category. But as I told you before, we were playing with duals. So we are not constructing the category of representations because it's not well behaved. What we construct is the category of co-representations. Yes? This is why we get dual things with the forgetful functor. So, example, you give me a fine algebraic group, SLN. You take the category of representations. Say, the finite dimensional ones. So, or anyone, or the finite dimension. So, we have the forgetful functor is a fiber functor. So, who's the coend of that? Our object, the algebra of rational functions. So, all these objects that I was talking about the first lecture are coend elements. Yeah? In summary, this is what we have done today. Hopf algebras give rise to tensor categories with fiber functors. Yes, we have two ways of constructing a category with a tensor category with fiber functors is using representations or co-representations. We have the two dual scenarios, representations or co-representations, and you may choose between them, okay? If the thing is finite dimensional, never mind, you will get more or less the same thing. Yeah, they are equivalent. If the things are not finite dimensional, it's better to take the co-modules, the co-representations. How do we go back? We take the Tanaka-Klein reconstruction. So, what do we do? In the finite dimensional case, you take the representations and the forgetful functor. In the infinite dimensional case, you take the co-modules and the forgetful functor. You may also take, in the infinite dimensional case, the co-modules. Of course, you may always take the co-modules. So maybe is the better scenario to take always the co-modules of a Hopf algebra. And to go back, you construct the endomorphisms of the functor or the co-endomorphism of the functors. And the difference is, in one case you get one Hopf algebra, in the other case you have the dual. So you always construct the Hopf algebra, but they are one dual of the other. And the category in the theory of quantum groups, sometimes you get this object and sometimes you get these objects. In analysis, in operator algebras, one always constructs this object, the coends. Yeah? In the books of, I think I put a book about that. In the book of Matrix Compact Quantum Groups by Audrey, all compact quantum orthogonal groups or matrix compact groups or something like that is called the name of the book. I don't remember now, sorry. The compact quantum groups are constructed using the coend construction very explicitly. So if you want to see how to construct very explicitly the coend, look at that book, okay? Maybe for the next time I will give you the correct title. So it's very explicit. So this is why quantum groups appears in nature. So because they are related to categories, and the categories are everywhere. So this is all for today. Thank you very much for being there and listening. So we are now open to questions. So I have a big question now. A lot of them. The first question is, how do we find the finite condition of a tensor category without referring to a Hopf algebra? There is a way, as I said, that the category is finite if it is isomorphic to the category of modules of a finite dimensional algebra, not Hopf algebra. And you can look for some properties on the category for saying that. I was telling that I was giving you an equivalent formulation for that. But there is a way, it is in the book of Ettinghoff and Ettinghoff, Jelakin, Istrik, and Ostrich. But there is a way. Okay, the tensor category appearing in nature are fusion tensor, well, maybe not fusion, but all the categories appear in nature are given by conformal, how is the name? Quantum conformal field theories. To give a theory like that is given is by giving a tensor category or a fusion tensor category. Yeah, and you may look in internet. The way to construct the category is not by representations of anything; it's by diagrams like this. yeah, something like this, and how you may put together and something related to the tensor, when putting together diagrams like this are related to tensor products, and things like that. Yeah. So there are a lot of examples of categories playing with drawings and diagrams, and they are not maybe the representations of something. The idea of that something, the category is representation of something, is reconstruction theory, and sometimes one wants to know more information about that. Is also related to categorification of rings. Yes? But we have a lot of these categories that a priori, in physics, you know the category, but you don't know the algebra. And so you have to reconstruct the algebra. So most examples of quantum groups comes from the reconstructions of this type of algebras. The most well-known is the UQ of SL2 that I'm going to talk about the last lecture. And other ones, yeah? This is just one example. The three. This is a very nice question. How many fiber functors do we have? We can have a lot of them. One way to relate the fiber functors is via tensor equivalence. So you have a fiber functor that do something and another functor that do another thing, but there is an equivalence between the images. If you have this equivalence, it means that in the Hopf algebra, you have a twist. So there is a definition of twist elements, and different tensor factor, different fiber functors are related by a twist. And the thing is, how many fiber functors do we have? Then, for knowing that, you have to know all the twists. So you have to classify twists. What is a twist? A twist is actually an element in the tensor product. So it's called always a J. It's an element of the tensor product, which is actually has to do with cohomology. It's a two co-cycle in a certain cohomology, cohomology. So it's not, there are some papers about that, how to classify two co-cycles for some objects. Is because you are classifying tensor structures. As you ask, you could have a lot of tensor structures. It depends on the cohomology class of the co-cycles, of the twist. This is a twist element. And the thing is, in quantum group theory, one open question or a question, general question is, how many quantum groups can we have? Can we have multi-parameter quantum groups and things like that? The answer is, it depends on all the possible tensor structures. Okay? And the tensor structure depends on the twist. And okay, so one way to produce new examples of quantum groups is by finding twist. So this is why in the theory we have a lot of results and papers about twisting quantum groups. Okay, I think I'm going to, if instead of algebraic representations we take some analytic representations, okay. Yes, if you take a smooth representation of a Lie group, then you will have the same tensor category. And if you want to recall the smoothness of the category, then the smoothness or the analytic part is given by the first thing is to have a proper representation category. You have to have a unit, or what I was saying, that the tensor category, a unit. For that, you need compact groups or locally compact groups, because you need the unit. If not, the unit is not a function because you cannot integrate the unit so well, so you have problems. Yeah, the integral of the unit is infinite dimensional. It's infinite. So for compact or locally compact groups, quantum groups, this is the way we talk about it. There is, what was I saying? How to represent these compact or locally compact things. Then you have first to have an involution. And the compact things are the things stable by the involution. So the involution is a star structure. So you talk about star algebras. So by doing analysis, so for compact things is related to star Hopf algebras, star algebras. Yes, algebras with an involution called star. With compact quantum, if you put quantum in the geometric side, then you have to put Hopf in the algebra side. And if you want to keep the analysis here, then you have to complete here. And this is called by C star Hopf algebra. You have to take completions of things. So here is completion with respect to a metric. And the idea is you take the completion of the algebra generated by the matrix coefficients. So you define first what should be the polynomials, which are the matrix coefficients. And that is okay. This is the algebraic thing. You have a star operation, and then you complete with some matrix, with some metric. Of course, you have different ways of completions. There is a completion with respect to one metric and to the other, and you get different quantum groups. Yes? This is the theory of compact quantum groups. Which is very difficult, more difficult than the algebraic one, I think. And the only theory that is known that has axioms for the definition is the one given by locally compact quantum groups. It was given by Kusterman and Bayes, I think, the definition. Yeah. So to that, what I was talking today, you had to add completion with respect to some metric. I hope I answer your questions, more or less. Are there any other questions, or yes? You're welcome. And very nice questions. I really like them. You're paying attention. Any other question in the audience, if there's anyone left? Okay, if not, see you in the lecture 3 and 4. And in the next lecture, we are going to talk about concrete examples of coordinate algebras and universal enveloping algebras. So, bye-bye.